How are we doing today? Today we're moving on in solution chemistry, starting our discussion on solution concentration. Today we're going to focus primarily on molarity. All right. For our level of chem, we will do molarity and parts per million. So parts per million will be the next day. Today we'll just deal with molarity. In college, if you move on to superchem, they'll deal with what's called molality. There's something called molarity and molality, which are not the same thing. I might discuss molality real quick when I do parts per million, but we're not going to do any problems with that. So molarity it is. So first things first is our bell ringer. So it says, according to reference table G, what are three substances whose solubility decrease as temperature increase? And then explain why they do that. Okay. So if you look at reference table G, so if you look here, this is reference table G. So three substances whose solubilities decrease so increasing temperature is going to the right. Things that go down as you go to the right would be HCl. All right, there'd be this line right here, which is NH3, and then this line right here, which is SO2. All right, so HCl, NH3, and SO2 are all gases. So it says explain why these do that. They do that because gases solubility decreases as temperature increases. All right, so you can know that the HCl, the NH3, and the SO2 are all gases. Okay, real quickly, and this is something that I assume people know how to do, is how to make a solution. Kool-Aid is such a thing. All right, Kool-Aid is a solution. If you ever there's actually a proper order to doing it. We're going to do it in respect to chemistry containers. All right, whether you do it in a pitcher at home, that's fine as well. All right, but these flasks right here, these are called volumetric flasks. All right, and whatever the volumes are, these ones are 1 liter volumetric flasks. They measure for 1 volume and 1 volume only. Okay, you can't get like half of a liter in these things. You can only get 1 liter. You get or 3/4 of a liter. They are very, very precise for 1 volume. So we have like 1 liter ones, half a liter one, tenth of a liter ones, and all different size volumetrics for this purpose. All right, but to make any solution, doesn't matter what the solution is. All right, whatever your solute is. So in this case, our solute is sodium chloride. You put the solute in first. All right, so the one that's in lower quantities, usually for us in chemistry, a lot of times it's a solid, sometimes it's a liquid, very rarely is it a gas. All right, so you put your liquid solute or your solid solute in the container, okay? And then you're going to add the solvent up until the final volume. All right, you can't, so for like this case right here, if you're making 1 liter of the solution, you can't put 1 liter of the solvent in and then add the solute because depending on the interaction between the solute and the solvent, the volume can increase, and sometimes the volume can actually decrease as well. So what we do is we add our solute first, then we add enough solvent to get to our volume that we're trying to achieve. So in this case, we're trying to make 0.769 molar solution in 1 liter of it. All right, we'll go over that, how to do that in a minute. But basically what that means is we have to take 45 grams of sodium chloride, and put it in the container. And then we're going to add enough water to fill it up so that the bottom of the meniscus is at the mark on our flask or our container or our jug if we're making Kool-Aid at home, or the cooler if it's a big thing or whatever. So that's the order of operations. Standard operating procedure for making a solution is add the solute, fill with solvent, mix together. Okay? All right. So supersaturated solutions. We did talk about this. I'm going to show you what I think is a pretty cool demo next week when everybody's in school or most everybody's in school. All right, but this little simulation right here, I think it'll run again. There we go. These are the reusable hot packs. All right, and these are the ones that like you boil to get the, when you see it here as a clear substance, it's a liquid. They're clicking this little disc, which adds a burst of energy, and then this white stuff is actually solid, and it turns solid. And when it turns solid, it actually gives off heat, so it's exothermic. All right, so this is an example of what happens to a saturated solution when you mess with it, so to speak. All right, so saturated solutions contain more solute than normally can be dissolved. All right, they're unstable, and this thing here is unstable. You can boil it or put it in a microwave so that it redissolves, so it turns back into a liquid. But as soon as there's that little disc in there that you snap that gives it a little bit of energy. Sometimes if you just drop it, it will do it as well. All right, so they're unstable. So that supersaturated solution is only temporary. All right, and really the only way you can get a supersaturated solution is you warm the solvent, you add enough solute to make a saturated solution, and then let it cool down. And if that stuff will stay in solution, all right, as it reduces in temperature, all right, it's now got more dissolved than it normally would hold. All right, the other way, which is not the easiest thing to do, is let it sit long enough so that some of the solvent will evaporate off. But more likely than not, you're going to make a supersaturated solution by adding solute to the solvent, making a saturated solution, and letting the solution cool down. Okay, it doesn't normally work just to add some more in and stir it up. It's because of the instability of the stuff. Not every substance at our, what I would call our normal air conditions, pressure and temperature, will supersaturate. There's very few things. If you've ever made rock candy, it's kind of like it. All right, it's similar, but not necessarily the same thing. Okay, so here we go. Examples of solutions, some terms that we may or may not remember, and I just always want to point them out in this unit. First thing is an alloy. Alloys are mixtures of metals. All right, so they're solutions of metals, and they're mixed together for various reasons, whether it's strength or price or flexibility or rigidity or lack of corrosion or whatever it is. All right. So brass, you know, people who play brass instruments or brass doorknobs or things like that, those are mixtures of zinc and copper. So to make that, it's in a certain percentage, and we're not going to worry about that. They take zinc and copper, they melt it, mix them together, and then you get the properties of brass. All right. We've already talked earlier in the year about gold jewelry. Is a mixture of gold, silver, and copper. Depending on the proportions, you get white gold, yellow gold, or rose gold. All right, so those are alloys as well. Air, the air around us is a mixture. All right, you should know that it's primarily nitrogen, then carbon dioxide, then oxygen, then other filler gases at very low percentages. So it's about 80% nitrogen. I think it's like 16% carbon dioxide, a couple percentages of oxygen, and then some other gases. Okay. All right. So air is a solution as well. Solution is just a mixture of things. And then aqueous. So once again, revisiting this term. All right. Aqueous is when things are dissolved in water or water is the solvent. All right. So abbreviation in chemistry, you have to know this. Anytime you have a subscript AQ, that means it's the substance before it dissolved into water. So that's sodium chloride dissolved into water, which is basically salt solution. This is salt water. Okay, there's lots of different salt waters. This is just salt water with sodium chloride as the solute. Here we go. We got C6H12O6, which is glucose, if you remember from living environment. All right, glucose aqueous means it's glucose dissolved into water. So that's just not like a piece of sugar. That's sugar dissolved into water. Okay, so you do have to recognize at this point in the spectrum that you know that the AQ means it's dissolved into water, or it's a solution where water is the solvent. Okay, here we go. Now we flip the script to concentration. So concentration, it describes the amount of solute per solvent. All right, it's the relative amount of solute to solvent. So subjectively, we can say things are more concentrated or less concentrated, or dilute versus concentrated. All right, if you've ever made orange juice from orange juice concentrate, or you look at a package when you buy orange juice, it'll say not from concentrate. Some people think that's better than if it hasn't been concentrated or whatever. But what they do to concentrate orange juice is, let's say the oranges grow in Florida. We want orange juice here in Syracuse. So instead of shipping a lot of the mass of the orange juice is water. So what they do is they concentrate the orange juice stuff. They basically boil off the water. So you get this orange juice concentrate, and then we'll come back up here. They ship just the concentrate. We come up here and we rehydrate it with water, or reconstitute it is another term that is used. Okay, so that's a concentrated, really super concentrated, and then the dilute form would be the form that we actually drink. All right, objective, we can actually put numbers to this. We can put values to this. All right, molarity is a concept that's only used in chemistry, all right, where it's moles per liter, because not a lot of people know what moles are, but it's universally used around the world in chemistry. Another one that's used more primarily in the real world, like in the world outside of chemistry, is parts per million or parts per billion, depending on how small the concentration is. All right, we've talked, well, we haven't really, because we haven't had class this year about it, but Onondaga Lake, the lake next to Destiny Mall, they measure, and every lake they measure things, but a lot of the pollution they measure in parts per million or parts per billion to see if it's suitable for, fishing or swimming or whatever. All right, the actual water in the lake is actually fairly clean. It's the sediment that's been remediated, and it's pretty good right now, but I don't know if And people get all nervous about it, but that water is connected to Oneida Lake as well. So it does mix with Oneida Lake, but it's diluted by it gets to that point in time. But anyway, so those are concentrations. So we have subjective, you say something's concentrated, objective, we can actually put a number on it. And today we're going to work on the molarity side of it. Okay? And both of these formulas are on your reference tables. I'll bring them up once we use them. So if you look up here, so this is just like a picture to represent concentration. So we've got the picture of what we would see with our eyes. And then we got down here like a representation of what happens with the particles. All right, this one I think everybody would agree would be the least concentrated or the most dilute. This one would be the most concentrated or less dilute. And the difference in the particles, so if you look down here, the red particles are the solutes. So you know the light pink color here is primarily solvent particles with just a little bit of solute in here. When you start moving up the grade levels here, you get a little bit more particles in here, and then the super concentrated one has a lot of particles in it. It's not like you have equal numbers of solute and solvents, it's just that you get a more concentrated version of that. Okay, so dilute, concentrated, dilute, concentrated. Okay, solutions can be dilute or weak or more concentrated like we just said. Molarity is a way to express the concentration. Molarity is abbreviated capital M. You have to be careful with that. Can't use a lowercase m. You can't use a lowercase m written big because lowercase m means mass. So you got to be careful with your m's. So the formula for molarity, which is on your reference tables, is the number of moles of solute over liters of solution. So you have to make sure you're in liters. All right, if they give you the volume in milliliters, you have to be able to convert it. If they give it to you in kiloliters, you have to be able to convert it. If they give it to you in hectoliters for some reason, you have to be able to convert it to liters. All right, it's a standard unit for molarity. And then we revisit this moles stuff that we've done already before. The moles formula is on your reference tables. The number of moles is the mass divided by the GFM. So here we go. We'll make it simple. If you have 2 moles of something dissolved in 4 liters of solution, what's the molarity? So here you got 2 moles over 4 liters. So 2 over 4 is 0.5 molar. Okay, so that is as simple as it can get. Moles over liters. Now, a lot of time we don't give you moles, or they don't give you moles. They're going to give you grams. You have to convert to moles. Sometimes they'll give you it not in liters, and you have to convert it to liters. So you just got to be careful with that. You know, attention to detail, like anything we do in chemistry. So here we go. So we have a problem here. So here we go. We got that same picture up here. So we got these dissolved particles, which is sodium chloride here. Sodium is the black one and chlorine is the red one. So how many moles of sodium chloride are contained in 250 milliliters of solution with a concentration of 1.25 molar? Okay. So this is where we start. So we know we have to use the molarity formula, and because it talks about, actually we're not going to go past that. So we use the molarity formula. So molarity equals moles of solute over liters of solution. So they give us, it says how many moles. So they want to know how many moles. They want to know this one right here. So are contained in 250 milliliters of a solution. So we have liters of solution at the bottom, and they tell us the concentration is 1.25 molar. So here for M, we're going to put in 1.25. Moles of solute is going to be our X. And then down here, we have to put liters of solution, but the problem is they give it to us in milliliters. So we have to convert to liters. Remember, King Henry died by drinking chocolate milk. Milliliters, there's 1,000 milliliters in every liter. So what that means is we have to move the decimal point to the left 3 places for milliliters to get to liters. So you're going to move the decimal point 1 place, 2 place, 3 place, so you're going to get 0.25 liters. So what I did here is I put the 1.25, molarity means moles over liters, so I put moles over liters equals X over 2 to show you that we're going to actually cross multiply to solve this. So to solve this, also it's 1 times X, which is liters, that's fine. And then 0.25 times 1.25, and that's going to give us 0.313 moles of sodium chloride. All right. Now another problem, they can make this problem a little bit more challenging and say, well, how many grams of sodium chloride it is? And then you would have to take this number of moles and then convert that to grams using the mole formula. So I'm just trying to let you know where we go or where problems go with this. Okay? All right, so that's problem number 1. Problem number 2. What volume of solution will contain 15 grams of sodium chloride if the solution concentration is 0.75 molar? So once again, we're starting off with, we have the molarity formula. Molarity is moles over liters, but we only have the molarity. We don't have the moles, and they want to know what volume it is, so we don't have the liters. So, but they do give us 15 grams of sodium chloride. So given us 15 grams of sodium chloride, we can figure out how many moles it has. And then we can use that moles in the molarity formula. So molarity is moles over liters. They give us 0.75. They want to know liters, which is X. And they don't give us moles, but they give us grams. So we can convert grams into moles. All right, we convert grams into moles by taking the mass and dividing it by the GFM. Now, NaCl's GFM is 58.5. Sodium is 23. Chlorine is 35.5. When you add those two together, you get 58.5. So you go 15 divided by 58.5 gives us 0.256 moles. So that gives us a number to put in here in the top of our molarity formula. We know the molarity is 0.75 molar, so we can put that down here. And then we don't know what liters are, so that becomes our X. Now, once again, separated by an equal sign, this really could be over 1. So you got X 75 over or 0.75 over 1 equals 0.256 over X. Cross multiply, and then divide, and then you're going to get 0.34 liters of solution. I'm not going to go over the algebra for that because that's something you guys should know. All right, so 0.34 liters, and I left it at 2 digits because this only has 2 digits. Okay, that's problem number 2. So I'm trying to give different types of problems. Problem number 3. All right, so here we go. We got 12.6 grams of sodium chloride dissolved in water, making 344 milliliters of solution. Calculate the molar concentration. So calculate the molarity. All right, so we need the molarity formula. Oh, well, I didn't do that yet. They don't give us moles. They give us grams. So we have to convert grams to moles. That's the mole formula, which is the moles equals the given mass, which is 12.6, divided by the GFM of sodium chloride. Sodium is 23, chlorine is 35.5. You add them up, you get 58.5. So the number of moles is 12.6 divided by 58.5. You do the math, you get 0.215 moles. Now, this doesn't answer the question. That's not the molar concentration. So we have to keep going using the molarity formula. So now we know how many moles. So we know 0.215 moles. We know a volume, but the volume is not in liters. The volume is in milliliters. So you got to convert this to liters. So it becomes 0.344 liters because you got to move the decimal point over 3 places. All right. And then you just divide these two numbers out and you get 0.625 molar NaCl. I know I've thrown stuff at you kind of quickly here. All right. But the expectation is you guys can do it. You can pause the video. Go back and look at it again if you want to. All right. Have a great day.